Right. Factors to take into account when looking at the viability of industrial processes. Now, this is really more from the old syllabus, but I left it in because I think it's interesting. If somebody's setting up a nitric acid plant, an ammonia plant somewhere around the world, obviously these are the things that they start to look at. So, how can you get the raw materials, the cost availability, the capital equipment is the machinery, the actual physical equipment you have to buy. So initially in these projects, there's an enormous investment. And how long will that equipment last also? Catalysts, how much catalysts cost, availability, and their life cycle. As we know in the Haber process, we use iron beds and they have to be changed. I think it's every 3 or 4 months because they become slowly poisoned by other things that might be in the reactants that creep in and they attach to the active sites and they don't want to leave. So they poison the catalyst by essentially reducing the number of active sites on the catalyst. With respect to the chemical process, the cost of the conditions they have to be maintained, pressure and temperature, energy requirements, atom economy, hazard. So essentially what are the dangers of the materials you are using or making and what accidents could happen. How green the process is. Green. Sustainable raw materials, that old stuff. We're all used to this now. Interestingly, 20 years ago, this wouldn't have been an important point. But now, obviously, there's a new atmosphere of awareness about the effects that we're having on the planet. And this really is one of the key things when setting up new plants around the world. The yield of the reaction as well, obviously, how much you're going to make of your product has to be taken into account. So there'll be somebody at the control desk in an ammonia plant constantly playing around to try and increase the yield of ammonia. And there may be other factors which influence this viability, but I think we've covered the main ones. Right, last thing in this section, we're going to get a little bit mathematical now. So imagine this general reaction. The little letters are the stoichiometric coefficients. Okay, so the number of moles you've got of each of these things. A plus B, B C plus D, it's a reversible reaction. So then at constant temperature, okay, at constant temperature, then this is the expression. The square brackets mean concentration of that particular component. So square brackets, that would be the concentration of C in moles per decimeter cubed, concentration of D in moles per decimeter cubed. And what we do is we raise each of these concentrations to the power of the stoichiometric coefficient in the equilibrium. Okay, this gives us a constant, and that constant at constant temperature is called Kc. It's called the equilibrium constant, Kc. Sometimes called the equilibrium law. So in exam questions, typically they'll say, give the equilibrium constant for this reaction, and you have to be able to reproduce it. This is important. And NB, depending on how many factors, how many components we've got in the numerator and denominator, the units of Kc will change. But that doesn't matter. It's the number. This is very chemistry, you know this. A couple of interesting things about Kc is the units change according to the reaction, but it's just the number we're interested in because, well, I'll talk about that in a second. And the other thing is the constant changes. It's a constant that changes only with temperature. Temperature affects the equilibrium constant. Okay? So it's a temperature dependent constant. It's great, isn't it? And the units don't really matter. But if you think about this particular reaction here, this is an intuitive thing. If this was an industrial process, you'd want Kc to be very big because you want lots of lots of products to be made. So the bigger the Kc, the better. So essentially the chemist here is not looking at the units. they're worried about, for a given temperature, how much of C and D are going to be produced. So you want a big Kc. Big Kc is better. Right. A couple of little things to add to this. So heterogeneous systems are systems that, well, they contain components that are in different phases or states. We're going to talk about states here, really. So for here, so heterogeneous systems, they are systems that contain chemicals which are in different states. Well, you know, the three states we often come across are solid, gas, and also liquid. Okay? The concentration of solids is considered to be constant, so that we don't put them in the equilibrium constant. We don't put them in the expression. So here you can have a go at this. Here, the equilibrium constant would be what? Have a try. The concentration of a pure liquid can be considered to be constant in a system that involves gases. So if you've got a pure liquid, there's one exception that comes to mind, but almost always, if you've got a pure liquid in a system, then we consider that concentration in a gaseous system, or in a system that contains solids, we consider the liquid's concentration to be constant too. Now, that's something, unfortunately, you're just going to have to accept. So here, the equilibrium constant Kc, well, we don't include the solid in the expression, and we don't include the liquid in the expression. So have a go at writing the equilibrium constant. There's more explanation of this on these pages, and you can try the questions too.